Good afternoon. I'm Gregory Binford. I'm not here in my role as the chairman of the board of Genesian Corporation. I'm actually here in my role as a fan of Stephen Wolfram. And I'm going to try to say as very little as possible in the next half hour so that he can say as much as possible. First question to you is basically Wolfram Alpha and AI.
So, we built this thing called Wolfram Alpha that I hope many of you have seen. It's a thing that, thanks. We're proud of it. Its kind of goal is to make as much of the world's knowledge computational as possible. And sort of, the way it works is just got a little input field, and you type in your question, and it's supposed to go and sort of get all the knowledge that we as humans have accumulated and figure out how to compute from that knowledge an answer to your particular question. So one might think that this is an activity very much like kind of AI, and it's been sort of interesting to me in sort of imagining doing this project over the course of many decades to kind of compare it with the things that people think about in terms of AI. I mean, I must say that I thought about trying to build something like Wolfram Alpha probably when I was a kid, and about every decade I'd sort of re-looked at the question and asked, do we actually have the raw material that we need to do something like this now? And I finally concluded that with our Mathematica system and with a bunch of ideas from the science that I've done, that it wasn't a completely crazy project to try to embark on about 5 years ago. But sort of the approach that we've taken is different from what one might think of as the traditional AI approach. I would characterize the traditional approach as being, we as humans seem to be quite smart and able to do lots of kinds of things. Let's emulate the way that we figure things out, and let's make a computer do those kinds of things more efficiently, and that way we'll make something that can do things like answer questions and so on. And so, if confronted with a physics problem, one might think, sort of the AI approach would be, let's try and think about it like a human, student of physics would think about it, try and reason about this or that thing. The approach of Wolfram Alpha is quite different. It's to say, let's leverage on the few hundred years of progress that's been made in kind of formal physics. Let's just try and find the best, mathematical method or whatever to solve the problem, and then let's just sort of blast through to the answer to that problem in a way that it isn't like human reasoning. It's just like take the science that we've accumulated and apply it and get to the answer. I mean, it's the same thing has happened with many kinds of AI-ish types of things, that one finds sort of an algorithmic approach that manages to kind of blast through the answer without doing it the way that we think humans do it.
Is it mostly brute force or something more subtle?
I don't think it's. It depends what you mean by brute force. I mean, there's many pieces. I mean, it's for example, understanding the kind of funny language that people choose to type into a little input field that's sort of like natural language, but it isn't like the way that humans would communicate with each other, because humans communicating with each other have a certain local context. The context is different when you're communicating with with an input field of a computational knowledge engine. Figuring out how to process that linguistic input, that's a whole adventure that actually leverages greatly on this on the kind of science that I've spent a long time developing. I mean, basically, the idea that something like Wolfram Alpha should be possible, that it should be possible to encapsulate a decent fraction of kind of computable knowledge in a system, is something that, I think I got to realize that might be possible from a bunch of things that I did in science, where I was sort of interested in to what extent can we encapsulate all the things that we see in nature in terms of simple computational rules. It's that sort of observation that kind of works for nature makes one think, okay, maybe there's a finite enough set of rules and so on that one can use to sort of understand natural language and to be able to sort of generate knowledge and so on.
Huh. Well, can you see any limits to this method?
Well, I mean, it's leveraging on what, in a sense, what Wolfram Alpha is doing today is it's leveraging on the last few hundred years of science and technology and trying to encapsulate those ideas. The real challenge is to go beyond sort of what we've learnt in sort of our human development over the last few hundred years of science, and to be able to sort of invent and discover things on the fly. And that's where I think things get really interesting. I mean, I think that one of the things that I've been interested in is the automation of that process, and I guess one of the big adventures there has been, from the kind of science that I've done, been interested in asking the question, if we just look at, for example, computer programs. We're used to computer programs that we as humans kind of engineer and construct. We say, okay, I want a program that's going to do this or that thing. So then the human sits down and they step by step create a program that has little loops in it and recursion and whatever else to perform the operation that they set out to perform. So I got interested many years ago now in kind of more the sort of the natural science of programs. If you just pick programs at random, all possible programs of a certain kind, let's say, and say, what do they do? You just kind of sampling this kind of computational universe of possible programs and asking what their behavior is. Now, you might have thought when the programs that you're looking at are simple enough that the behavior they would show would be somehow sort of correspondingly simple, that there wouldn't be anything very interesting that happens. Yeah. The sort of the big discovery from looking at cellular automata and other kinds of simple programs is that you can have a really simple program, and yet what it does, when you look at it, seems extremely complicated. To me, this is sort of an intuition-breaking discovery, because, you know, as a human used to trying to build things, I'm used to the idea that if I want to make something complicated, I have to go to a lot of effort to sort of build the thing up in some complicated way, do lots of work to make the thing complicated. But what it seems is that, you know, in this computational universe of possible programs, there's lots of programs that are really simple that just by their operation produce incredibly complicated behavior. Now,
yeah. As with, say, fractals or...
Well, fractals are a very specific case where you're just sort of dealing with something where you have sort of progressively nested pieces, but kind of that sort of a run-up to what you see in, for example, simple cellular automata, Turing machines, you know, any of the kind of models of computation. I mean, I think that the part that when we look at these things, one of the things that sort of got me excited from a sort of natural science point of view is, you know, when we look at nature, one of the sort of big mysteries of nature is, where does all this complexity that we see in nature come from? How does nature manage to make all this complicated stuff when we as humans find it very difficult to do that? I mean, when we, you know, if we're shown two objects and we're told, you know, one of them's a natural system, one of them's an artifact, yeah. The best heuristic is, you know, to know which is to say the one that looks simpler is probably the one that we, with all of our civilization and intelligence and effort and so on, created, and the one that looks more complicated is probably the one that nature, seemingly effortlessly, managed to produce. And I think that the point is, what's going on there is that in the case of the things that we produce today with our current technology, we're used to engineering things in such a way that we can sort of always foresee at each step what the result of that step will be. So we're sort of constrained in what we produce. We're usually constrained to sort of follow historical patterns of engineering, and to just always do things where it'll never get out of control, so to speak. It'll always be the thing we put in will always be able to foresee what it does. Well, nature doesn't have this constraint, at least most of the time. So, you know, it just goes and sort of, in many cases, I think, sort of samples this computational universe of possible programs, and then it's just, you know, an abstract fact about things that, out of all the possible sort of abstract programs that exist, a decent fraction show really complicated behavior. Now, what's interesting, and the thing that I've gotten excited about in recent years is, so you've got all these programs out there in the computational universe, and some of them do really complicated, interesting things. The question is, can we mine that computational universe for things that are technologically useful to us? Yes. So, you know, it's kind of like if we look at the, you know, at the world of materials, right? We see, you know, there's magnetic rocks, and there's, you know, liquid crystals, and there's all kinds of things, right? We discover these as a matter of basic science, and the question is, can we can we find that these things, can we find a match between what actually exists in nature and some technological purpose that we have? And so one of the things that I've done a lot, and it's actually a core piece of technology inside Wolfram Alpha, actually increasingly also inside Mathematica, is just this idea of go out into the computational universe and go find simple programs that turn out to be useful for particular purposes. So, one of them might make random numbers really well. One of them might be really good at doing some kind of, image recognition. One of them might be good for doing certain kinds of linguistic analysis and so on.
Can you use natural, or rather artificial selection in this computational universe?
So, I think natural selection is I do things in a dumber way most of the time, in the sense that what I've found is that if you really want to be creative, you just have to sample this computational universe completely at random. Because as soon as you're doing things incrementally, in a kind of natural selection sort of way, you're constraining yourself to not go too far away from things that more or less work.
Yeah.
I mean, it's just like, it's an interesting question when we think about biology in relationship to the computational universe, and we ask, if we look at biology, how much of the computational universe of possibilities, of possible programs, has biology sampled?
Yeah.
How much inside us, which programs is it sampling? And I think natural selection is actually the force for simplicity in biology in many ways, because natural selection operates best on these things that are almost, calculus-based, where it's, this bone gets slightly longer and eventually the thing becomes a biped or whatever else. But it's sort of a continuous variation of things. I've been interested, I tried to look at some kinds of biological organisms to ask the question, if you look at sort of the space of possible organisms of a particular kind, to what extent does it cover the space of computational possibilities? So, my favorite is mollusk shells, okay? If you've probably seen where sort of the question is, you have these mollusk shells and they grow in a little spiral pattern and they make pigment patterns on their shells. And the issue is, if you look at there are different possible programs, essentially cellular automaton programs that they could use, and you ask the question, out of all the mollusks of the Earth, how do they sample that space of programs? And so far as I can tell, they pretty much sample all corners of a particular space of programs. So it's as if the mollusks of the Earth just sort of randomly pick a program, and then they sort of print the results on their shells. So that's a case where there doesn't seem to be much natural selection going on. It seems like what we see is just sort of a reflection of the sort of abstract stuff that exists in the computational universe.
And that it's incremental everywhere, and so you could just move continuously.
Well, I think in other cases where we see, an issue would be I think it's an important issue in this computational universe of possible programs, the ones that we sample in our own sort of operation, what slice of that space of possible programs is the set that we sample. So one of the phenomena that occurs in these programs when there's complicated behavior is this thing I call computational irreducibility. The question is, you've got this program, you're running it, you say, what will this program do after 1 million steps? So one way you can find the answer is you just run the program for 1 million steps and see what the answer is. But if you think you're a really clever math person or something like that, you might say, I can just solve the problem and I can find an exact solution to what's going on. And I can say, tell me how many steps it's going to run. I can just plug things into a formula and immediately work out what the answer will be. And that's what a lot of theoretical science has consisted in doing, is trying to make these sort of predictions where we can, use our cleverness to sort of outrun the actual behavior of the system. Well, one of the things that happens in the computational universe is that you don't get to do that very much. A lot of these programs have this phenomenon of computational irreducibility. Essentially what happens is these programs, even though they're really simple, there's this thing I call the principle of computational equivalence, which basically says once it's a sort of an empirical principle, I think it's true and we're getting more and more evidence for it, but for now it's really an empirical principle that sort of says once a program is doing something that isn't obviously simple, it's probably equivalent in its computational sophistication to any other program. So a side effect is that once you have a program that is doing something that isn't obviously simple, it's probably capable of being made into a universal computer. It's probably capable of being... So what that then tells one is, we think of ourselves, we think of this little program and it's doing its thing, and we think we're really smart, so we should be able to figure out what this program is going to do much more efficiently than it does it itself. But this principle of computational equivalence says that that's not true. It says that we are basically equivalent in our computational capabilities even to these very simple programs. So that means that kind of our ability to sort of outrun the program and be smarter and predict it is just not going to happen. for a lot of these programs out there, there's this phenomenon of computational irreducibility that means that we're sort of stuck. The only way we can find out what the program is going to do is effectively by running the program and seeing what happens.
Right.
So now the question is, for example, in computational biology, for instance, if a lot of the processes that go on there have this feature of computational irreducibility, that's a problem in terms of us being able to do engineering. It means that we sort of have to do simulation. It puts a lot of pressure on having the best possible models that we can simulate in the most efficient way, because we're going to have to simulate them. We're not going to be able to find an exact solution and sort of just invert the problem and sort of immediately be able to jump to the end.
So there may be in future technologies a kind of an analytical horizon, and you can only go beyond it with simulations.
I think so. I think that will be. I think one of the features of, if I look at the things that we've mined from the computational universe to do things in Wolfram Alpha, for example, what you have there are programs which humans do not understand. They're programs that we can prove that they do what they're supposed to do, but if you look at it, it's not operating in some way that's, some simple loop, some nested pattern, something like that. They're doing their thing. They're often doing it very efficiently. I think that's probably typical of many of the efficient ways to do things, that they don't have the kind of simplicity that we tend to have in our engineered structures. And so I think, one of the things that's going to happen with technology in the future is as more and more technology gets found by basically just mining the computational universe, it's going to be less and less human understandable. A bit more like the way that nature is right now. Nature isn't particularly human understandable. And so, and I think what's going to happen is, in current technology, there are many things that we do. I don't know, if you look at, how do we transport people? We have trains that run at specific times, this kind of thing. We can imagine that, when we put more computation into the thing, we'll end up with a much more sort of irreducible situation where there are little things that are just in time kind of running around and optimizing what's going on. And sort of looked at from the outside, it's just going to look like this very complicated process that is sort of irreducible to us. It won't be understandable in the way that current technology tends to be understandable.
So it will look metaphorically like Mexico City, in which transport is dominated by jitney cabs and not by trains or streetcars.
Right, but I think that the issue is to what extent, as we look at future technology, so there are many things that change as you get your technology from mining the computational universe. Another one is that sort of innovation is free, in the sense that, for example, we had an experiment a couple of years ago called Wolfram Tones that is a thing for just creating, originally ringtones, although it turns out to have been much more of interest and use to composers and things like that, producing things more elaborate than ringtones. But kind of the idea is, go out into this computational universe and just sort of sample, find programs, and find programs that produce this kind of complexity, but nevertheless complexity that's based on some sort of logic and rules, and translate that into some kind of musical form. And, it takes a millisecond to go and find, to create something that is quite competitive with what humans can create for sort of a short thing like that. So I think one of the things that will happen as we kind of get things from mining the computational universe is that we get to sort of customize things, we get to innovate and create things, that is no longer the issue, that's no longer the expensive step. I think the real challenge is usually when we have this, there's a vast supply of kind of wonderfully innovative, wonderfully sophisticated, efficient programs out there. The big challenge is to match up what those programs do with human purposes, with what it is that we actually want to do. That tends to be the problem of technology in general. Match up what exists in the universe with what we as humans want to be doing. And I think it kind of gets us into a strange kind of direction of thinking about when we have in sort of the limit of technology, where we've got all this very efficient stuff, and maybe we've managed to, we have to sort of ask ourselves, how do we distinguish what we've created from things that sort of just exist in nature and so on?
So you see in the future it'll be harder and harder to actually have a sense of the natural, because it won't be clear.
Yes. Now we have a sense of the artificial. As I say, when you compare an artifact with a natural thing, there's history. There's tons of history in these artifacts that we make. They have, they've got circles in them. They've got, all sorts of things that are, that come from the long history of mathematics or science or whatever else. I mean, I think that that's, in a sense, it's interesting to kind of think through, how do we get, this question of natural versus artificial, brings up things like SETI, right? There's the question of...
My next question.
When we see a signal from the cosmos, how do we tell if it's the result of, some huge civilization that got built up and eventually it figured out this is the great signal to send, this is the signal that's going to prove we're smart to everybody else in the cosmos, right? Versus something that's just a simple natural process. Well, one of the things that comes out of this principle of computational equivalence thing that I studied a lot is the idea that actually there probably isn't ultimately a real distinction between those things, because the limit of our technology ends up being this thing that has all this computational irreducibility, all this complicated computation going on, but so does nature. And so, we know the sort of anecdotes like, Marconi, right, had this, would go across the Atlantic in his yacht, right, and he heard all these funny whistlings and things from which he picked up on his radio masts. And he thought, okay, well, he didn't think that seriously, actually. Tesla thought more seriously that these things must be transmissions from the Martians, because how could there be such a complicated signal that was made by something natural? Well, it turned out it's actually, the Whistler mode. Isn't it? It's some kind of modes in the atmosphere.
Yeah, it's a plasma helicon, right.
So it's the plasma is being sophisticated enough that it's sort of producing this thing which could at least fool somebody for a while. And then, it's really a question of, and what we realize in the end is that these processes, whether they're happening in a plasma, we say things like the weather has a mind of its own, by which we mean, what we realize is that statement is not quite as goofy as we might think from modern science that it is, because really these processes, these computational processes, are as sophisticated as the processes that probably go on in our brains and so on. And making a distinction between sort of that computational sophistication and the computational sophistication that we have, that's a tricky business. And I think in the end, it ends up being a very history-dependent definition. I mean, it's just like, if you're asked, what is life? Okay, you say, well, we know what life is. We can tell. We have a living thing. We have a non-living thing. The living thing has, RNA. It has cell membranes. It has all kinds of stuff in it, right? But what's the essence of something being alive? That's less clear. Of life that's existed on Earth, and we know how that works. But if you're presented with something else, people had definitions. The Greeks said, if it can move itself, it's alive. Okay, that went away when there were machines that could move themselves. Then it was, something that could reproduce itself, something that could have some particular chemical signature. All of these things were replicated with technology. And the only definition we get left with is this essentially historical definition that says it's the thing that comes from this whole thread that's existed. So I think the same will happen with intelligence, that you can make computation, raw computation is actually not that hard to make. The issue is it human-like computation? Is it computation that has the sort of same thread of purpose and history that we have? And it's a slightly different question. It's actually easy, I think, to make something that's sort of as smart as we are. It just doesn't have the same. It doesn't have it's not like us in the sense that it has the same sort of history and purpose and so on.
It won't have our brand. That inevitably leads to the big question, which is perhaps the most complicated thing in the universe is in the head, but also in the genomics. So how is all this going to have an effect on genomics? A revolution is now just exploding. What can we expect?
Well, you see, I think one of the sad things about the principle of computational equivalence and these kinds of things is that the conclusion is that what's in our head and in our genomics is actually not that much more sophisticated than what else is out there. Yeah. We have the same problems and so on. But I think that the thing that when we get to try and make technology that can intervene for medical purposes and things like that, clearly, computational irreducibility is a big pain in the neck as far as this is concerned, because it makes it much harder to know what the consequences of things will be. Right. I mean, I know in a quite different area, worth mentioning because it's kind of fun, you think about this computational universe of possible systems, and you can ask the question, our physical universe, is it one of those computational universe of possibilities? So, if we take our physical universe and we say, can we search for our physical universe out of the space of all possible universes, right? So this sounds like kind of a crazy thing to do, but actually I've spent quite a bit of time making that, I think, a lot less crazy. It's a real thing, and what's really bizarre about it is it turns into a big software engineering effort to try and actually build what you need to represent these very abstract things that are sort of below space and time, and that you have to try and build up to how something that might be recognizable in the universe. Well, the real bad thing is that this computational irreducibility phenomenon really bites one. Because you have this little candidate universe, and you say, I look at these universes, and you say, okay, we've got thousands of universes today, let's look at each of them. Some of these universes are complete losers. They after a few steps, they just go splat. They have some feature that is, obviously not our universe. But even within the first 1,000 universes you look at, I can tell you that there are universes that kind of bubble around and do complicated things, and you can trace them for 1 billion steps, and they're still bubbling around and doing complicated things. And because of computational irreducibility, I don't know whether those universes are our universe or not. So,
Yes.
It could be that we kind of have to rely on some degree of computational reducibility, because we can't, in our computer, emulate the actual 14 billion years or whatever. So we have to rely on some degree of computational reducibility. But this is a case kind of, this is probably a worse case than biology. It's sort of interesting that in physics, we sometimes have thought that physics is in the current, physics is somehow more fundamental and somehow a more necessary kind of science. And biology is the science where things are kind of just particular, where it's the particulars of history. And I think maybe the actuality is the opposite. That is, that in biology we're actually sampling a decent chunk of the computational universe, whereas in physics, our particular universe, bizarrely, is just one universe in this computational universe. That's it's interesting well, it's a fun thing to explore, but not the topic. But you were asking about, in terms of, I think the critical thing for sort of the genomics, sort of systematic systems biology, things like this. The critical thing, as far as I can see, is what are the sort of computational primitives that are the important things that we need to represent in the way that biological processes happen. Should we be thinking about Boolean algebra? Should we be thinking in terms of simple programs and the complicated things they do? It's worth realizing that in the history of biology, there are these times when sort of a paradigmatic idea has been kind of critical, and it's looked like everything was just incredibly complicated, like in genetics before 1953, right? All these phenomena, all these different things, just incredibly complicated. Everybody was saying, we'll never understand genetics. It's just there are too many different effects, et cetera, et cetera, et cetera. And then this kind of organizing idea of digital information and DNA and so on came along, and immediately kind of there started to be a framework in which one could understand all this stuff in genetics. So a question, I don't know if it's the case, it could be that this sort of what we see in the computational universe, what we see with these simple programs and the dynamics of simple programs and so on, that is the paradigmatic thing that we need to be able to sort of make the same kind of progress today on all the sort of systematic problems of aging and all these kinds of things, sort of analogous to this digital information idea of before. I don't know if that's the case. The devil is in the actual details of the biology, and whether it's right to represent things in terms of these simple programs, how the simple programs are sampled, what the role of natural selection is, whether natural selection is more like us as humans, picking only the engineerable programs, whether it's more like the particular example of the mollusk shells where it seems to try all of them. I don't know.
Yes. Well, okay, then. Remember, Einstein famously said he wondered if God had any choice in making the universe. So what's your money on?
Oh, that's a complicated question. So in this idea that sort of our universe is one of the ones sampled from this computational universe of possibilities, it feels very non-Copernican to say our universe is number 1017 of this whole space of possibilities. So I've been very interested in this question of out of a space of possibilities, where do the things that we know about live? So, for example, I've been interested in mathematics, where you can ask the question, there's lots of possible axiom systems for mathematics, but we have particular axiom systems for, geometry, algebra, arithmetic, and so on that we use, logic, and so on. Where do those lie in the space of all possible axiom systems? And is there something special about them? So I happen to know, for logic, out of all the possible axiom systems, the logic that we use is about the 50,000th axiom system out of all the possibilities. So it's not number one, it's not number a quintillion, it's about 50,000. And what we realize from sort of looking at that sort of a view from above mathematics, so to speak, is that the mathematics that we have today is sort of a consequence of the history from Babylon and so on. Of, people invented arithmetic and geometry, and then those got generalized, and that's mathematics. And mathematics is really a historical thing, even though we thought it was this formal abstract thing that would cover everything. Well, so now the question is, for physics, if we know this computational universe of all possible universes, where's our universe out of all those universes, right? And one of the things that we might say, well, we're not, we're just a random universe out there, okay? We might be the gazillionth universe, okay? We actually know we're not, because the most obvious thing about our universe is that there is order in our universe. It's not the case that kind of the rule for the universe is kind of as big as the universe, and every piece of the universe just gets to do its own thing. We know that the rules for the universe are quite small compared to the universe, so to speak. And so, so that kind of tells us we're not out in the sort of the far infinite reaches, but, how small are we at? Well, okay, I have a hypothesis about this. My kind of, to me it's very unsatisfactory to say our universe is, it might be true that our universe is just number 1017 in the enumeration of possible universes. If we know that, who knows what we would then conclude after that. But I have a feeling that the true answer to this, where is our universe in the space of all possible universes, will be something more bizarre than we've possibly thought of. And actually, my guess right now is that what will turn out to be the case is that out of a large collection of these possible universes, they are all in some bizarre sense equivalent, and that actually our actual sort of existence, and I haven't figured this all out, otherwise I'd be able to explain it better, but our kind of that it has to do with the interaction between us as observers in these universes and the actual dynamics of the universes themselves, and that somehow within a large class of these universes, they're all precisely equivalent in every detail, once you sort of factor out the fact that the observer has to be themselves within this universe, watching the sort of dynamics of the universe itself. So my guess is that the answer will be that the question was the wrong question, and that the real answer is there isn't a serial number, because sort of all these universes are somehow equivalent.
I see. So you end up grading the question.
Yes.
Okay. Well, thank you, Stephen.